circular time shift property. Why it is circular? Because since x of n is a periodic sequence and whatever the shift you are going to perform, the time shift it is a circular in nature. So that's why it is called as the circular time shift property. So similar property we have seen in case of the Fourier transform, the DTFT, and even the Z transform, Laplace transform we have seen. But there we are not use the term called circular. Why? Because it's a normal sequence, but it's a periodic sequence. X of n is a periodic sequence. That's why you're going to call it as the circular time shift property we're going to call. So let us look into the statement of the property. So if the DFT of x of n, so the statement always usually goes like this, x of k. So then the property says like this. So the DFT of x of, so we are going to perform the shift in the time domain, and that shift is circular in nature. So that is we are going to call it as a mod n. So this is equivalent to the, so the DFT of the sequence x of n is x of k multiplied by omega into the power of k into m. So we are going to add the Twiddle factor. We are going to multiply in the frequency domain. So this is what the circular time shift property. Here k can take the value from n minus 1. So in order to prove this one, let us consider the proof of this property. We'll consider the proof of this property. So in order to prove this one, we'll consider the DFT formula, the IDFT formula we'll consider. So that is the IDFT of x of k, which is nothing but, so it's a x of n. So it is 1 by n into summation k is equal to 0 to the n minus 1 x of k into omega n to the power of minus km. Omega into the power of minus km we are going to consider. So omega into the power of minus k into n. So that is called as the IDFT formula we are going to consider. So minus k into n. So minus k into n we'll consider. Now what we do, so since we want n minus m we want here, so we are going to replace n on the both the sides. We are going to, this is a small n on the formula. So you're going to replace the n with the n minus m. So because we want that one, so replace n by n minus m on both the sides here, on both the sides. Both the sides we are going to replace the n by n minus m. So wherever n is there, we are going to replace the n minus m. So it has become x of n minus m. So this is equal to the 1 by n summation k is equal to 0 to the n minus 1 x of k into omega into the power of minus k into n minus m will get. So on the LHS part, we got the required quantity. Now we are going to apply the exponential law of indices. We are going to apply. So it has 1 by n summation k is equal to 0 to the n minus 1. So x of k will expand the Twiddle factor here. So it is omega into the power of minus k into n into omega into the power of plus k into m will get here. So this one is the IDFT here. The IDFT of the sequence x of k is the IDFT of the here, whatever the shift you are performing on the LHS part, this is a circular in nature. So we'll write one term. Since the shift is a circular, shift is circular in nature. So because it's a circular here, so we can write this one as x of n minus m modulo n we can write. So this is equal to the 1 by n summation k is equal to 0 to the n minus 1 x of k into omega into the power of minus kn into omega into the power of so we can rewrite this one as the IDFT of this term x of k into omega into the power of km, which is equal to the x of k into omega into the power of km. So this is equal to what? X of n minus m mod n. So or else we can write this in terms of the DFT formula. We can write as, so that is the DFT of x of n minus m mod n. So this is equal to the x of k into omega into the power of k into m. So this is what the property which is called as the circular time shift property. So similarly, we can rewrite this property. Similarly, we can modify this property here. Similarly, we can modify this property for this is the right shift, and similarly we can write for the left shift also. So the DFT of x of n plus m mod n. So this can also be written as, so since minus is there, that's why the plus came here. So since here it's a plus is there, so we can write as the omega into the plus k into m. So this is for the right sided sequence. The property is called as the time shift property. So these properties will be helpful in order to find the DFT of the sequences. Where if you know the DFT of x of k, if you know, and if you want to find out the shifted version of the x of n, and where we don't know the sequence x of n, at that time we can make use of that property. So let us consider one problem where that kind of case will be considered here. So we'll take one problem here. Suppose if take the problem. So the problem is if DFT of x of n is equal to x of k. So this x of k is nothing but something like 10 or 2 minus 2j minus 2 and 2 plus 2j. Okay, so here we need to find the DFT, okay, of x of n minus. Here we need to find the DFT of the sequence x of n minus 2 mod 4 we need to find out here. So here we don't know the sequence x of n, we don't know, but we know x of k here. So in this time we can use since the length of the sequence is n is equal to 4 is it, so we can assume this is equal to the 4-point DFT. So n is equal to 4, it is assumed as a 4-point DFT. So from the time shift property, here only the time shift property is there. So it is x of n minus m is there, the DFT of that one is, so x of n minus 2, x of n minus 2 mod 4, which is equal to the, when I take the DFT of this one, so it has become x of k into omega 4 to the power of 2 into k will get here, 2 into k will get. So that's a DFT here. Let us call this is equal to the y of k, one term which is equal to the y of k here. You're going to call this as equal to the y of k. So in order to find the DFT, we can substitute k is equal to 0 to the 4. So it is x of k into omega 4 to the power of 2 into k. Omega 4 to the power of 2 into k, we'll substitute here. So since we know omega 4 to the power of 2 is minus 1 here, so we can rewrite this one as also as x of k into minus 1 to the power of k, we can do substitute here. Let us substitute k is equal to 0. So it has become y of 0 is equal to x of 0 into minus 1 to the power of 0. So x of 0 is 10. We got the, and similarly when I substitute k is equal to 1, we got y of 1 is equal to, so x of 1 into minus 1 to the power of 1. X of 1 is 2 minus 2j. When I multiply with minus 1, it has become minus 2 plus 2j. Similarly, let us substitute for the k is equal to, let us substitute for k is equal to 3, k is equal to 2. So this has become y of 2 is equal to x of 2 into minus 1 to the power of 2. So this has become minus 2 into 1, it has minus 2 only. So similarly, k is equal to 3, we'll substitute here. Y of 3 is equal to the x of 3 into minus 1 to the power of 3. So it is it will become -2 minus 2j will get. So let us write the y of k. Let us summarize that one. So it is 10. So -2 plus 2j -2 and -2 minus 2j. This is